Welcome to lesson number 3, vertical projectile. Lesson number 2 was very long. We were focusing on the velocity time graph, and towards the end we wanted to demonstrate the velocity time graph where the ball or the object have got many bounds. But because the video was too long, we had to cut. So this lesson number 3, we're going to start from a velocity time graph where a ball is bouncing. Then we can come to the position time graph. So I wanted time, I will just give you a scenario, then I draw the graph. Let's say we have, this is the person who is on the ground, then the person throws a ball up, then the ball comes down. Then the ball return back up, but you can see that when it returns back up, it does not reach the initial height because it lost energy in the form of sound and in the form of heat. That's why it's no longer have enough energy to return to its original position. Then the ball bounced again. The ball bounced again. The ball bounced again. Then it came to rest. So this is it. I can say this represents the position. Then this represents the time. Let's take one different something like this. I'll give them something like this. Okay. Then the ball was thrown up, it bounced. So these spaces, they represent the contact time. That is the time a ball was in contact with the ground. So this is 0 minutes, then the ball return back after 10 seconds. 10 seconds. Then this is 12. Then this is 18. This becomes 20. Then this becomes 26. These are seconds, right? Can you see? The ball was projected up, then it returned back down after 10 seconds. Then you can see that there is space here. Then when it went up again, the stopwatch was at 12 seconds, meaning that it was in contact with the ground. It was in contact with the ground for 2 seconds. That is 12 minus 10 seconds. That is going to give us a 2 seconds. So this ball was in contact with the ground for 2 seconds. How do we know? Because when it touched the ground, the time was 10 seconds. When it returned up, the time was 12 seconds. Meaning that the ball was in contact with the ground for that 2 seconds as we subtract 12 minus 10. Here is the same scenario. When this ball went up for the first bound, when the ball went up, it was 12 seconds. When it returned, it was 18. So if we want to know like the time at which the ball went up and returned, we are going to count how many seconds from 12 to 18. It means we're going to say 12, 13, 14, 15, 16, 17, 18. So it means it took only 6 seconds. Isn't it? We're counting from 12 to 18. So from 12 to 18 is only 6 seconds. Then the ball went up again when it was 20 seconds, meaning that it was in contact with the ground for 2 seconds. That is 20 minus 18. Then when it returned to the ground on the second bound, it was 26. So if we want to know the time at which the ball went up and came back to the original position, we just count from 20 to 26. That will be 21, 22, 23, 24, 25, 26. It means this ball from this point until it returned back, it only took 6 seconds. Again, it took 6 seconds. You understand? Although it will not make sense according to real life situation, because if it took 6 seconds going up, this one surely to no longer take the same time. Or let me change it, because I'm the one who's making this scenario. Let me say 20, then 24. It's 24. It returned back when it was 24. Now, the contact time remained being 2 seconds. But the time it took for the ball to go up and return back to its original position, it will only be 4 seconds according to this. Okay, so I want to show you how to draw a velocity time graph when you have a scenario like this. This is a position time graph. They sometimes said a question which will come like this, and they will ask you things like contact time. Contact time, it is this space which represents contact time. If there are no spaces, it means there is no contact time. If you find something like this, it means there is no contact time. And it is not like that in reality. It's just that this is physics. Some of the time we ignore certain things. So if there is no contact time, it means these graphs, they do not have space in between. And I've already demonstrated to you that if there is no contact time, how you write or how you must write your graph. Okay. So now let's say this ball was projected up at what can I say, at 15 meters per second, meaning that when it returns, it will also be 15 meters per second. Then when it went up, it was projected up, it bounced and it went up again. It is not projected this time, it's a bounce. It is a first bounce. Remember I told you that to bounce is to return back up, because you know that these English words, sometimes they confuse us because English is not our home language. So it's very important that we also master some of the key words for English so that we know what it means in terms of physics. So when we talk about a bounce, we're talking about when a ball touches the ground and returns back up. That's why I'm saying this is the first bounce, this is the second bounce. This ball only bounced only two times. You understand? So we're saying that the ball bounced and returned back to the ground at 8 meters per second. Meaning that when it comes back, it will return to the same position at the same velocity. You know that, as I've already demonstrated to you. Then the ball went up at 4 meters per second. Then it means even here it will be 4 meters per second, because the ball is coming back to the same position. I hope you understand. Notice that the things which I'm writing, it's numbers which I'm creating myself, so that I can show you how to draw a graph when you're given a position time graph like this. So it is not like anything which I'm teaching you. I just decided to come up with my own numbers so that I make a demonstration. So now let us go to the main business. How do we draw a graph which represent this position time graph. So we're going to draw a velocity time graph. This is a position time graph. So the velocity time graph for this position time graph, it is going to be like this. We're going to have the axis. So our axis is going to be like this, and this is the time. The time is in seconds. Then we're going to have the velocity, which is in meters per second. And this is our 0 time and 0 velocity. I've already demonstrated that this is the negative x-axis, and this is the negative y-axis. This is the positive y-axis, which one will just shows anyone that we want that we are taking going up as positive, or we are taking going up as negative. Meaning that if you want to take going up as negative, you are going to start your graph this side on the negative side. Or if you want to take going up as positive, you are going to start your graph from this positive side. I've already demonstrated to you that. So now we can draw this graph. So do not be confused. These graphs, when there are bounces, you draw graph one by one. Don't try to make any sketch you will represent these things at the same time. Just draw this one. You act as if we don't have this. You act as if we don't have this. You draw this alone. I will tell you how to represent this contact time and everything. So we're going to start. It means I can say this is 15 meters per second. 15 meters per second. This space from 0 to 15, it must be equal to also this one. This will be 15 meters per second. These two spaces, they must be what? They must be equal. I think 15 is around there. 15. So you must use a ruler to make sure that the spaces between they are equal so that they give you the right shape. So since this is 15, remember that if the ball was projected at 15 meters per second, when it was going up, when it comes down and return to the same position, it will be moving at 15 meters per second. So this is what is going to happen. I told you that as an object is going up, as the object is going up, what will happen to the velocity? As the object goes up, velocity decreases. Meaning that whenever we represent a graph, velocity time graph of an object that is going up, it means that the line of the graph will be approaching 0, because as the object is going up, velocity is decreasing. So we're going to represent that the object is going up, and as the object goes up, velocity decreases. I must draw a small graph so that I do not waste up space. So as the object moves up, the velocity is doing what? Is decreasing. That's why as the object is moving up, the velocity is approaching 0 until finally the object reaches its maximum height, where its velocity is 0, and it is represented here. So as the object is moving, is going up, the velocity is decreasing and becoming 0. That's why I'm saying that the object was projected up and it moves at 15 meters per second. But as it moves up, it will be decreasing its velocity. It will be 14, 13, 12, 11, 10, 9, 8, 7, 6, 5, 4, 3, 2, 1, 0. 0 will be here. Understand? So as the object is moving up, velocity is decreasing. Then the object will do what? The object will come down. As the object is coming down this side, what will happen to the velocity? Velocity will start to increase, meaning that the straight line graph of a velocity time graph will be moving away from 0 as the object is coming down. So that is what is happening here. You can see that the straight line graph is doing what? It's moving away from 0. Then we're done to represent the the first part. So you can see that when it hits the ground, the object is moving at 15 meters per second. Right? So here we need to write everything. We know that the ball from 0 minutes, or from the time it was projected up until it returned to the ground, it took how many seconds? It took 10. So here we're going to have 10. But from 0 time until its maximum height, how long did it take? We know that going up and coming down, it will take the same time. So it means if we want to know going up and coming down, it means it took 5. So it means here will be what? 5 seconds. This is the maximum height. Understand? This is at the maximum height. Now, we want to represent this contact time, and we want to represent the second bounce. The first bounce, I mean. How do we do that? What we do, we can see that this graph has ended here at 10 seconds. What do we do? I usually tell the learners that it's like you are taking this y-axis. You see this y-axis? You take this y-axis and you put it here through this line. You see this line? So we're going to have a new y-axis. You see where this graph has ended? You've drawn a line, right? So you continue that line, and that line goes up like that. It becomes the y-axis. So what is it that you did? You just simply took the y-axis and then you moved it forward. Seems as if my y-axis is not straight. You must draw a very straight line using a ruler. You can see myself, I'm not using a ruler to make my demonstration. You can see, right? So that is what is happening. I'm holding a cable here. This is my y-axis, can you see? So, since I have my y-axis here, I drew the first graph, right? I drew, it means triangle here. I drew the first graph. Then, my y-axis is here. Then, I check this y-axis. I come and put it here. Can you see now? It means I have a new y-axis. That's then I'm going to start the new graph. It's like I'm ignoring the first graph, then coming to the new graph with a new y-axis. It's like I ignore this, I don't see this. I have a new y-axis which looks like this one. Then I continue to write my new graph. Then, what we need to notice is that there is a space. There's a space between the two graphs, and this space is because of the contact time. The time at which the graph was in contact with the ground. So, what you need to do, you know this is 10 seconds, right? Somewhere here will be 11 seconds, somewhere here will be 12 seconds. Because time does not stop to move. It means that you're not going to start to draw your graph here where the graph is going to touch the y-axis. No. It will be different from this one. Your graph will not touch the y-axis. It will just move 2 units to the left, which is your right as you're watching this video. The graph is going to move 2 units to the right. It's going to move this side. Why am I saying 2 units? Because here we have 10 seconds, then 11 somewhere, then will come to 12. So it means the graph will shift 2 seconds from the y-axis. You understand? The y-axis has just ended here. Then we have a new y-axis. So your graph must shift 2 units here. So that's why I'm going to shift it 2 units. You see, I'm going to start to draw my graph here where there is 12 seconds. I'm not going to start here. If this graph, there was no contact time and it was represented like that, you can see that there is no contact time. It means when I draw my graph, I was going to start from this very y-axis. I was going to start from this y-axis to draw my graph because there is no space here. You understand? which is not possible in nature, because when the ball bounces, there will be always contact time. So if there was no space, it was represented like that, I was going to start my graph here. But since this graph, as it is given now, there is a space. So it means I need to start after 2 seconds. So the ball bounces back and it went up at 8 meters per second, meaning that I must find the 8 meters here. You understand? So I'm going to make correct points by using my ruler. You understand? So it means my 8 is somewhere here. My 8 is somewhere here. You understand? Here is 8 seconds. Even here in the negative side, my 8 is going to be here. You see, this is 8 seconds. Meaning that the ball was projected up at, it bounced back up at 8 meters per second. Then it means I'm going to start here from here. It means I'm going to start here. 8 is at this point, right? Notice that I've said that you take the y-axis forward, but you must not write numbers here. You use these very same numbers. So it means I'm going to start here. Remember that when the ball is going up, its velocity is going to decrease, meaning that the velocity, if it has decreased, the straight line graph will be approaching 0. That's what is going to happen. So it means I'm going to draw my graph being like that. It is approaching 0 as the velocity is decreasing. The velocity is now 0. Understand? The velocity is now 0. This is at this point, the maximum height. This represents the maximum height at this point. So when the ball is going up, its velocity is decreasing. So the velocity visit time graph, it will be approaching 0 as the ball is going up until it becomes 0 meters per second. That's why you see this graph decreasing, approaching the x-axis. Okay, so now what will happen after the maximum position? The ball is going to come down. When a ball is moving down, its velocity increases. That's why the velocity versus time graph will be moving away from the 0, the x-axis will be moving away because velocity is increasing. Okay, then it will move away. It will be increasing. See, it will be increasing until it reach what? Until it reach 8. And you see that it has reached 8, then it reached 8, then that's what we have. Then we plot everything. The maximum height, how many seconds did it take to reach the maximum height? Remember we said that this ball, when it went up, it was 12 seconds. When it came down, it was 18 seconds. So notice, I'm not going to write 12, 18 here. I'm not going to do that. I'm not going to write 12, 18. What I'm going to do, because time does not stop. Time does not stop. You understand? So I need to make my correct representation here. So the contact time is what? Is 12. The contact time is 12. So how many seconds did it take to reach up? I'm going to half. You understand? The half here. What is the time? Which is between 12 and 18. It's going to be 12, 13, 14, 15, 16, 17, 18. Meaning that it is going to be 12, 13, 14, 15. It means the half is what? Is 15. So at the maximum height, it will be 15 seconds. It means here we have 15 at this point. You understand? Then when the ball returns back to the ground. When the ball returned back to the ground, the time was 18 seconds. So it means here it will be 18. And I think this graph is too obvious. It is too obvious the way it is represented. Okay, you can see now that we are left with drawing the last demonstration. You can see that we are left with drawing the last demonstration. We are left with drawing the last demonstration. I'm trying to adjust and make sure that you write the correct thing. Understand, right? Okay, your graph must be clean. Your graph must be clean. So let us demonstrate the second bounce. How do we demonstrate the second bounce? Please bear with me. Let me erase this part so that I can have enough space to make this demonstration. Okay. So this is our x-axis, and this is the time in second. Time in second. Okay. Then we need to represent this. We need to represent this. We need to represent that. So what do we do? The ball then bounced back up again. It went up at 4 meters per second. Meaning that between 0 and 8, 4 is going to be in the midway between 0 and 8. You see that? Then there is contact time. Can you see? So what do we do? We have the what? We have the new y-axis, which is here. We take this axis, y-axis. We move forward with it and we put it here. So we have established another new y-axis. Can you see that? We have established a new y-axis. Then we are going to use that new y-axis. How do we go about it? There is contact time, meaning that we're not going to start to draw our graph here. Our graph is not going to touch the y-axis because there is this time, the contact time. What is the contact time? The contact time is 2 seconds. Can you see that? Meaning that I'm going to space 2 seconds. It means this is going to be 18, 19, then 20. I'm going to start from 20. I'm going to start when the time was 20. Then the ball was, it bounced back up and it was moving at 4 meters per second, meaning that I'm going to have my 4. It means it is going to start here. Then it went up. When it was going up, you know that as the ball is moving up, the velocity it slowly becomes 0. So as the ball is moving up, the velocity is approaching what? Velocity is approaching 0. The velocity is becoming 0, and finally it becomes 0 at the maximum height. You understand? So at the maximum height, the velocity becomes 0. Then you can see then the ball returns back to the ground, and as it returns back to the ground, what will happen to the velocity as the ball is moving down? When a ball is moving down, the velocity of an object is going to increase. So when we draw that on a velocity versus time graph, we need to represent that by showing the velocity of a ball increasing, moving away from the x-axis. As in the x-axis is at velocity 0. Then the ball moves down and our graph is going to end here. Can you see that? Can you even draw this? Graph is going to end here. Then it will be like that. Then how long did the ball take from 20 seconds to 18? So it means we're going to have 22. It was 22 seconds. How do we know that it was 22? It is the center between this. Understand? Between these 2 points. Then it was 22. When it returned back to the ground, it was 24. So that's how, this is how to represent a graph where there are bounces. If they give you a graph, these spaces, the reason that where spaces, the graph never touch this y-axis is because of the contact time. So these spaces represent the what? The contact time. So whenever you see a graph like this, just know that this is a ball that was bouncing. So this is a ball that was bouncing. So ladies and gentlemen, I hope you understood how we draw a velocity time graph of a ball that is bouncing. If there are no contact time, it means that you're going to start drawing your graph from the y-axis like this. So when it is like this, it means there are no contact time. As you can see that the graph are starting from the y-axis. But if there was contact time which is these spaces, it means that you need to leave what? The space. You need to leave the space like that. Thank you, ladies and gentlemen. I hope this was useful to you. Let me quickly make a demonstration of a position time graph. Let me make a demonstration of a position time graph. Position time graph is what we've been drawing ever since I started to teach you. Whenever you teach vertical contact time, you teach it through a position time graph. So position time graph, it simply represents the position, the distance between the ground and where the ball is. So here, we're going to have the time in the y-axis, which is independent. Then we're going to have the position in meters per second. That position is the what? Is the distance. So if I can have 50 here, then I have this. Then I have that. What does this mean? It's a position time graph. What does it mean? What does it mean? It means that a ball, right? A ball was at height 50 meters. The ball was at 50 meters. Then it went down to 0 meters, because here we have 0 meters. So it means if it is a person who projected the ball down or dropped the ball down, you don't know if it was projected or it was dropped because there's no velocity. But what we know is that this ball was lifted up by 50 meters. So it means this is delta y. This is the displacement. It means our displacement is what? 50. Because this ball was lifted up by 50 meters, then it was dropped or projected down, and this time around, the delta y is what? Is 0 meters. So this is the position time graph. Okay. Let me show you another scenario of a position time graph. Let's say this is a building. This is a building. This is a building. Understand? Then someone is standing here. The person is standing here. The person dropped a stone. A stone is dropped down. A stone is dropped down. So it means this building or the position of the ball is at 60 meters. So if I want to represent a stone which was dropped down on a position time graph, what do? I just say this is 60 meters. Then the ball was dropped down. Say, I'm going to say drop down. When it was dropped down, it got to what? It got to what? It got to zero position. It went here where it is 0 meters. You understand? It went to 0 meters. Okay. What about when the ball is projected up? Projected up. The person is standing here, and then this person projects a stone. and it reached what? It reached 50 meters. Then return back to the ground. It reached 50 meters and return back to the ground. How do you represent that? It is easy to represent that. This video was broken into two so that we can be able to separate between the velocity versus time graph and the position time graph, which is complicated, and the acceleration time graph. So in the video which you just saw now, we were just starting with the position time graph. Let's just continue with the position time graph. Position time graph. So now on this position time graph, I'll just make a short example, then we'll go straight to a situation whereby we have got two objects which are thrown down at different time. When we have two objects which are thrown down at different time, we find that we throw the first object down, then after 1 second or 2 seconds we throw the second object, or we drop the second object or project it. As you know that to drop it means that the initial velocity is 0, but to project it means the initial velocity is a particular value is greater than 0. Okay, so if it's a person who is standing at the top of a building, then this person does what? This person projects an object, and that object goes up and it comes back. And you see that the person is standing at the top of a building, and this person project an object up, and that object comes back, but this time around it does not come back to where it is started. The person is standing at the top of a building. The person projected a stone up, and the stone fall on the ground. The stone fell on the ground. Okay, they tell us that this distance is 60 meters. From this distance to this distance is 60 what? Is 60 meters. The distance where the person is standing to the ground is 60 meters. Then this distance is 20 meters. It's 20 meters. From this point to this point is 20 meters. Right? So draw a position time graph representing that. Position time graph, we're just dealing with the displacement. So we're going to have our axis. We're going to have time on the x-axis. Then we're going to have the displacement. The displacement delta y in meters. We have delta y in meters. Here the time is in seconds. Then let us check. The object was projected up, but when it was projected up, it did not start from 0, because this is 0. It was not at position 0 when it was projected up. It was at 60 meters. So here we're going to have the 60. Then we have the 60. Then, how do we represent that? It was at 60 meters. Then the object was projected up, and it went up by 20 meters. So it means it's going to be 20 plus 60, which is going to give us 80. So it means at this point it will be 80. So it means if we want to represent that on a position time graph, we're going to show an object which is going up, then the object end at 80. At 80, then the object falls down to the ground where the position is 0. So we are able to represent that. We are able to represent that. We're able to represent that. If ever we're given time, let's say we are told that this ball was projected up and it took 0.3 seconds for it to reach this point. Then from this maximum height to the ground, it took 0.4 seconds. How do we represent that on this position time graph? It means from this point to this point, it means here we're going to have what? We're going to indicate the time. It took what? 0.3. To reach this part. Okay. Now I want to give you the second scenario for position time graph. You saw in that first scenario which I just gave you now. I hope you were able to see how I demonstrated it. Now I want to demonstrate a situation whereby we have two balls or two objects that are dropped down at different times. I want us to do that. So let's take we have a girl who is standing at the top of a building, and that person drops the ball and the ball hits the ground. The length of the building is 30 meters. This building is 30 meters. It's a triple story. The length of the building is 30 meters. Then the ball, let me say, ball A is projected, is dropped from 30 meter building. Ball A is dropped from a 30 meter building. Right? Then, let me write here. After 1 second, then. After 1 second, ball B is dropped. Ball B is dropped from the same height. It's dropped from the same height. Right? So, the last statement is that both balls reaches the ground at the same time. Both balls reaches the ground at the same time. This is a scenario that I've just created. I want to show you how to draw a position time graph for this scenario. We've got two balls, ball A and ball B. Ball A is dropped down and it reaches the ground. After 1 second, ball B is dropped down and both of them they reach the ground at the same time. It is possible while ball A is in the air, while it is moving, ball B is just dropped while ball A is on the air. So it is possible that then those balls they reach the ground at the same time. Understand? Both those balls they reach the ground at the same time. So now we need to draw a position time graph to represent that scenario. I hope now you got the scenario. Let me erase so that I can have enough space to represent that. Let me erase the wheels. The scenario is that we've got two balls, ball A and ball B. Ball A is dropped down from a 30-meter tall building, then it reaches the ground. After 1 second, when ball A was dropped, ball B is dropped. You understand? Ball B was dropped. You understand? Okay, so let us represent that on a graph, on a position time graph. We're going to draw our axis, then we're going to have the time in second, and we're going to have displacement. Displacement, delta y in meters. This is our x-axis, our y-axis. Then, let us start to represent. We know that all the balls were dropped at 30 meters. So, we can make our points. These 30 meters will be here, right? Notice that when you have 2 points, you need to make sure that the spaces on your graph are equal. Because this one is only 1 point, I can say that is here. It will not, there will be no problem. I can say that is anywhere. But if there are 2 points, I can't say that is here, 20 is here. They will be too close. It means I need to create the spaces. If I'm moving by 5, 10, 15, 20, 25, I need to move like that. If I have 2 points for distances, so that my graph does not fuse into, does not lose shape, you can say. So, we have got only 1 point, which is 80. So, I'm going to represent ball A. So, this is ball A. Ball A was dropped down. Ball A was dropped down. And this ball A, it touched the ground. You see? Ball A, it touched the ground. We don't know after how long. We don't know after how long. Let me make it to be even more bigger so that I can make my points. Yes. Ball A, isn't it? In my scenario, I did not give the time. So we know at time X, which we don't know, the ball will touch the ground. At time X, the ball will touch the ground. So 1 second, I can say 1 second is here. This is 1. 1 second later, 1 second later, what happens? So 1 second will be here. The ball B is dropped down from the same height, meaning that this ball is being dropped from the same height. Remember, it's dropped from 8. So we need to represent the second ball. After 1 second, the second ball is dropped. Meaning that the second ball is dropped from what? It must start from this point. It will never start lower than 30 because it was dropped at what? At 30. So when it was dropped, it started to what? To move down. To move down. Then, look what happened. You see, the 2 lines, they join and become 1 line. Why are these lines joining and become 1 line? You see, the 2 lines are joining and become 1 line. It's because these balls are going to the same point. We were told that they reach the ground at the same time. So they must join and become 1 line and reach the ground at the same time. Do you understand this diagram? It represents 2 balls. This ball is starting sort of in the air here because it was projected. It was dropped, not projected. It was dropped down. 1 second when ball A was already dropped or already moving. So that's why this one it needs to start here. You can see the ball was already moving. When it was at this position that I do not know, then the second ball was dropped. Can you see? So you can see that it is going to start at 30. It must start at 30. It must not start here because this point, it is not 30. It must start somewhere here. You understand? Then it is the ball are going to reach each other. Then they touch the x-axis at the particular time which were not given. So that's how we represent a situation where we have got 2 balls that are projected same time. You understand? Okay. So position time graph, they are not complicated and they are not difficult. So I hope you understood. So now we can look at velocity versus time graph, which is the simplest. Velocity versus time graph, which is the simplest. Not the velocity versus time graph. Acceleration versus time graph. Velocity versus time graph is the one which we have already done. I think it's a little bit complicated, that one, but it is easier to understand. So now let us do the acceleration time graph. This is the acceleration time graph. We know that the acceleration for a projectile is constant. It's a 9.8 meters per second squared. It does not change because it's a projectile. A projectile is an object which has been given initial velocity and it moves under the influence of gravitational force only. So this is the acceleration time graph. Acceleration time graph, which represents the acceleration. You can see as it stands here. So now we want to do an acceleration versus time graph. Let's say we have okay, I love buildings. I love buildings. Yeah, this one is a search house, a simple search house. Then someone is doing what? Is busy working here. A person is busy working here. Busy putting the glass. You know our houses have got glass, right? Then the person happened to drop something. Happened to drop something. Then that particular thing, it fell down. That particular thing, it fell down. So a person dropped something. A person dropped a hammer or a stone. The person dropped a stone. The person was working with a stone here. Then they dropped that stone by a mistake. It fell down. Draw an acceleration time graph. We know that since it's a projectile, that stone, it is moving under the influence of gravity only. It is a projectile. So how are we going to represent that on an acceleration time graph? The acceleration time graph, it is easy. So if I want to represent that on the acceleration graph, time graph, I'm going to have time here. The time is in second. Then here I have acceleration. Acceleration, the unit is meters per second square. Then this is the acceleration. Then I'm going to have my 9.8. So will the acceleration be more than 9.8 or less than 9.8? It will remain the same. It is 9.8 meters per second all the time. It does not change. So I'm just going to, as the ball is falling, acceleration does not change. It's become 9.8, 9.8. So that's how we can represent an acceleration versus time graph for when someone is standing at the top of a building and they drop something or project something. The acceleration is not going to change. Acceleration is going to remain being 9.8. It will not change. So this is the first representation and scenario. The only trick which we can come across for acceleration versus time graph, it is the trick of a bouncing ball, whereby the ball is bouncing. Although acceleration will always be 9.8, but there is something that we need to take note of. Okay, let's say, let me give you a position time graph which you already know. Someone is projecting, someone from the top of a building projected I mean, they dropped a ball. Then the ball bounced and came back to the original position. This representation don't just represent anyhow. They must have a meaning. And you see, this is the time, this is the time, this is the tower in meters. This is the displacement. So the ball was projected from the top of a building, it bounced. So let me draw an acceleration resistance graph for that scenario. For the acceleration resistance graph for that scenario, I'm going to have it like this. Then I have the time. Then I have the what? The acceleration. The acceleration here, which is in meters per second squared. So what will happen? As the ball is moving down, acceleration is 9.8, 9.8, 9.8, 9.8. But immediately it touches the ground. The acceleration will never become 9.8, but we do not know what the acceleration will be. It will depend if the object touches the, but obvious. When the object touches the ground, it becomes still, then it goes up. So when the object that touches the ground, acceleration will be 0 because there will be no change in velocity. But it will be 0 for just 1 second or a very small amount of time, 0.01 second, you see, or 0.0003. It will be just still for a moment. The acceleration will become very small. So this is what is happening. We're going to have our 9.8 here. Then as the ball is moving down 9.8, 9.8, 9.8, then when it reaches here, we don't know. Then it becomes 9.8, 9.8, 9.8. We know that acceleration will become 9.8 at any position of the projectile. So it means we represent that like this. It becomes 9.8, 9.8, then it reaches the ground. When it reaches the ground, we just, we can draw dotted lines there. To be precise, we draw dotted lines like this. We draw dotted, then we come. Then we have jumped is because we don't know the value that is here. There's no value, they don't know the acceleration that is here. You see? Then this space, it is represented by when the ball has touched the ground. Then when the ball immediately, it bounces and it is lifted up the ground, the acceleration will continue to become 9.8, 9.8. So that is how we represent acceleration resistance graph of a ball that is bouncing. If it can bounce again, we're going to represent it like that. Bounce again, acceleration continue. And then like that, we move. That's how we do the acceleration resistance graph. Ladies and gentlemen, if you have been subscribed to this channel, please make sure that you subscribe to support us to continue to make more videos. We are pushed by passion. That's what pushes us. We want to see you passing and we want to see you becoming successful. So we don't want a black child to fail or to struggle with physical sciences while we think we know and understand. So please go and make it possible by sharing the videos. Tell people about this channel. Subscribe. Don't just come and watch the videos without subscribing. Because when you subscribe, it causes the channel to grow. When you post things, they reach many people. And we're doing this video so that they can reach many people. So please support this channel by subscribing. Ladies and gentlemen, vertical projectile graphs ends here. Then we're going to do the last lesson for vertical projectile whereby we'll be doing questions which will be a mixture of everything and calculations so that we can make what we did in lesson number 1 to come to life. So we'll do previous question papers, answering questions with you. Ladies and gentlemen,